All right, challenge number 3. And challenge number 3 actually is related pretty closely to challenge number 2. And so again, we've got high blood flow. This leads to a decreased diffusion time. And what I mean by that is that there's less time for diffusion to occur. It doesn't change the length of time that's needed for diffusion to occur. It's just how much time is available for diffusion to occur. And ultimately, this is helping us. We need to make sure that we maintain arterial oxygen. So to start off, we've got transit time. Like I said, diffusion doesn't happen instantaneously. It takes time. Not a lot of time, but it takes time. And the rate of diffusion, so the speed that this happens, is affected by solubility, which that's constant for a gas, the thickness or distance that the gas has to travel, the gradient, and then the surface area. Okay, so under normal resting conditions, the pulmonary capillaries hold about 70 milliliters of blood. Okay, and that's just in the capillaries. We're not talking all the lung, but we're just talking about the pulmonary capillaries. Cardiac output is about 5 liters a minute at rest, which means that you've got about 83 milliliters of blood moving through your body every second. All right, and so that would mean, if you did the math, that a red blood cell spends about 0.84 seconds in a pulmonary capillary. And the way we figured that out is you just go 70 mils divided by 83 mils. All right, so since it takes, under these conditions, alveolar oxygen of 100, venous oxygen of 40, so that's a gradient of 60 with the surface area and all the other things, it takes about 0.4 of a second for equilibration to occur. And we see that here. Okay, notice that we flatline, or that oxygen stops increasing after about 0.4 of a second. Okay, so plenty of time. It's normally in there for 0.8 of a second. We're in there for 0.4, no big deal. Exercise, though, can cause some problems. Pulmonary capillary 70, cardiac output's 20. If it only increases to 20, so that's 333 mils of blood per second. Now we're saying a red blood cell only spends about 0.2 of a second. Okay, and so we'd be about here. All right, if that was all true. But like I said, it takes about 0.4 of a second. The nice thing is, we can change the amount of blood in the pulmonary capillaries, and this is through recruitment and distension, which we talked about in our last video. And so not only does that help with pulmonary pressure, it helps with diffusion. And so if we recruit these capillaries and we also increase their volume a little bit, that's going to allow us to have more blood in the pulmonary capillaries at any one moment. And so it's going to make it easier for diffusion to occur. So we can triple the volume in our pulmonary capillaries. So we'll say 210 mils, cardiac output's 333 mils per second. So that means a red blood cell spends about 0.6 of a second inside of a pulmonary capillary during exercise. And this is pretty intense exercise. So there's lots of time to equilibrate. We could even double that, almost double that, and still have enough time. All right. Now, hypoxia is going to change the gradient, so that's going to change things. How could that be detrimental or beneficial? Well, it says wait until November, but really you need to wait until the end of April. All right. So if you look at this figure here, we've got transit time. Remember, that's how long the blood cell's in the capillary. All right, we've got our arterial oxygen, and then we've got a capillary blood volume. Notice that we've got a certain point where capillary blood volume essentially plateaus, and at the point where, at this dotted line here, this is where, even though we've increased capillary blood volume, transit times decrease so much that arterial oxygen decreases. And so once the pulmonary system can't increase its volume, transit time will decrease, and so eventually we'll get to a point where arterial oxygen decreases. And so this changes from perfusion limited to diffusion limited. Okay, if we say someone is perfusion limited, that means diffusion can occur, complete diffusion can occur. We just can't get enough blood there to get enough oxygen throughout the body. When we're diffusion limited, that means we don't have enough time for diffusion to occur. Okay, because of the gradient or the surface area, or the blood cells are moving too fast, that sort of thing. And so Like it says here, the rate of diffusion determines the overall rate that oxygen is carried away from the lungs. Now, what's really interesting is that in some highly trained athletes, there's actually this lag between alveolar oxygen and arterial oxygens at high workloads. And we can see that here. Notice that this person's alveolar oxygen's going up, but their arterial oxygen's dropping down. We call this exercise-induced arterial hypoxemia. And in some cases, saturation can drop below 90%, which is a significant drop. It's not completely understood why this happens, but some potential causes are things that we've already talked about. So we've got VQ mismatch, we've got shunting, both intra and extra pulmonary shunting, as well as diffusion limitation. So any of these things would cause or prevent our alveolar oxygen from equilibrating to meet our arterial oxygen. So, 3 things that you need to be able to do at the end of this lecture.